Alright, this is 7.1, all about graphing exponential functions. So if you've ever heard of exponential growth and decay in a science class, this is the math side of things, alright? So things that grow exponentially are known as exponential growth functions, right? Things that decrease exponentially are known as exponential decay. All right, in their graph overall, it'll start off, as we move from left to right along the x-axis, it'll start off like, just kind of creeping along. And then at a certain point, all of a sudden, it'll just like zoom off and shoot way up or way down. Right, exponential decay is kind of the opposite. Right, it starts off really high up, and then it just gradually kind of like tapers off. So note that you cannot take, well, this will come into play later, right? The log of a negative number. So overall, where we're headed in this unit are logarithms and exponentials, and they are inverses of each other. Okay, just like multiplication and division are inverses, exponential functions and logs are the inverse of each other. So when it says you cannot take the log of a negative number, that'll become important later on in 7.3. Okay, the overall form of an exponential growth or decay function looks like this. F of x equals a, where a is a number, a times b to the x power. And it's really important to notice that only the b is being raised to that exponent's power. Only the b is, okay? A times b to the x power. If this number here, b, this is what these bullet points are saying, if let's see, this must be a number that is positive, okay, because if it were negative, we could get numbers that aren't real. It must not be equal to 1, because any number 1 raised to any power is always just going to be 1. Graphs will approach the x-axis or another horizontal line. They will never touch the line, and this kind of line is called an asymptote. The asymptote means a limit or a carrying capacity in a real-world context, okay? So a lot of information here. Domain and range are also going to come into account as well. Remember that domain is all your possible x values for a function. Range is all your possible y values for a function. To find domain, in general, we start with all real numbers, and then we just remove numbers from the domain that would cause division by 0 or causing us to take the even root of a negative number, because those things are undefined. Okay, the numbers that remain are the domain. For range, there's not an exact algebraic procedure for it. The best approach at this point is to look at a graph and approximate it. And we like to write both of these in interval notation. Interval notation. Okay. So here's an example. Let's just dive right in. We're going to plot at least 5 points, and we're going to plot its asymptote as well. F of x equals 2 to the x power. So we're going to make a table, right? When in doubt with graphing, just make a table. So what are some numbers that we would want to plug in here for x? We could plug in -1, right? 2 to the negative first power would give us 1/2. 2 to the 0 power, fun fact, anything to the 0 power gives you 1. Even 8 to the 0, or 100 to the 0, or -100 to the 0, all these things give us 1. Okay, it's a definition in mathematics. If we put 2 in for x, 2 to the first power will give us 2. Right? If we plug in 2, 2 squared would give us 4. 3, 2 to the third power would give us 8. Then we can start plotting these. Okay, plotting these on our axis, and we start to see this this rapid growth happen. All right, so be really, really careful when you're connecting these. We need to have a little bit of a curve to it, but then we're not going to go below the x-axis, okay? Because no matter what, if we plug in more negative numbers, there's no number that we're going to plug in that's gonna get us into negative territory. All right, so our graph is just going to get really, really close. Actually, I don't want it to touch. Okay, it's going to get really, really close to the x-axis, but it's not going to go through it, and it's not going to touch it. Okay. All right, and then we talk about plotting its asymptote. We're going to use a dotted line for this. Use a dotted line. Maybe we can make our dotted line green. And then we want both sides to have arrows. So let's see how this goes. Sometimes it doesn't like it when I do this. Here we go. Pretty nice. All right, and so here, pretend like there's not that little blip. We just have our horizontal asymptote is right along that x-axis. Okay, so let's formalize some things here. Our asymptote is a horizontal line here. Our asymptote is y equals 0. Our domain, if we look at our x values, along the x-axis, we don't have any restrictions, right? We could keep plugging in a bunch of negative x's, a bunch of positive x's, and nothing's going to ever make us be undefined. So our domain is all real numbers. And our range, if we look at our graph, what y values are we getting? We're getting all sorts of positive y values, but we're not ever going to get negative y values. Okay, so we're going to get numbers from 0 to infinity. Is 0 included? Are we ever going to get exactly 0? No, so we're going to put a parenthesis around it. All right, and that's our overall process for exponential growth and decay functions. So let's try to make a table for this one as well. All right, what numbers do we want to try to plug in for x? If we plug in 1, we get 1/4. If we plug in 0, we get 1. If we plug in -1, we take 1/4 and we raise it to the negative first power. We can flip it, right? We can flip it and it'll become 4/1 to the positive first power, which overall gives us 4. If we plug in a -2, then it's like we're saying this, right? We can flip it on the inside and we'll get 4 squared over 1 squared, which is 16. So we're not really going to be able to plot that one. I know this has to plot at least 5 points, but I think in your practice, you're only going to have to plot like maybe 2 or 3. All right, so let's plot these. Over 1 up 1/4, 0 up 1, -1 up 4, and then -2 up 16 would be way up here. So we're just going to kind of come down this way. See that? All right, and this is an exponential decay function. Okay, this is exponential. Why is my pen not working? Hello? Oh, now it catches up. Okay, and then if we look at our asymptote again, it is our x-axis, right? It's that horizontal line, y equals 0. Our domain is going to be all real numbers because we can plug in anything for x. Our range, if we look and see what values for y is our function giving us, it's giving us anything that's positive, 0 to infinity. All right, let's think about this one for a second. So what values for x up here are going to give us integers that would make sense for powers of 4. If we plug in 2 for x, then we get 4 to the 2 times 2 is 4 minus 1 is 3, which is 64. Okay, if we plug in 1 for x, then we get 4 to the first power, which is 4. If we plug in a number in between 2 and 1, like 3/2 or 1.5, then we get 16. Right? If we plug in 1/2, then we get 1. If we plug in 0, we get 1/4. So we're not going to be able to plot some of those, but it'll help us get an idea of if we're looking at exponential growth or decay. So over 1 up 4, over 1/2 up 1, over 0 up 1/4, and then if we were to plot over 3/2 up 16, we'd be way up here, and then 264 would be like way, way, way up here off the screen. All right, so overall our function is going to look like this. And remember that we're not going to touch the x-axis. Okay, not going to touch it. I'm not going to go through it. Like that. We have our asymptote. That is, again, the x-axis. We're approaching it, but we're not getting close to it. So our asymptote is y equals 0. Domain, again, is going to be all real numbers. Our range, looking at this, would be anything that's positive, not including 0. Okay. So in general, domain and range for these are pretty much going to consistently be negative infinity to infinity. And again, these are exponential functions because we can plug in anything for these x's up here. Okay, and then thinking about our ranges, right, 3 to the x, let's just plug in some of these graphs and see what we can get. Let's see. Let's go to this one. All right, if we graph 3 to the power of x, looking at this, we can see, oh, okay, our x's are all real numbers. Our y's are going to be those positives. Okay, so 0 to infinity, that's our range. See if we plug in 0.4 to the x power. We see the same range, actually. We see those positive y values. Okay, 2 times 10 to the x, this is that a times b to the x form that we haven't seen too much, but that works in general, a times b to the x. 2 times 10 to the power of x, we see again that's exponential growth. Okay, it's growth because it starts off small and then it gets really big really fast. Population is something that is modeled with exponential growth. So for most common exponential functions, the domain and range will end up being like these examples. We could do something fancy to switch up the range, but the domain in general is going to be all real numbers. So let's consider this graph. Okay, negative and then parentheses 1/4, closure parentheses, raised to the x power. Look at this. Okay, so it's like we've taken our exponential decay function and we've flipped it over the x-axis. So we still see that our domain is all real numbers. We could plug in anything for x, even though right here it looks like we're stopping at an x value, we will keep going, okay? But our range is what's going to be different because here we have a bunch of negative y's. All right, so our domain will be negative infinity to positive infinity. Our range, though, sorry, I don't know why my pen is being weird. Our range is going to be negative numbers, which we want to represent as negative infinity comma 0. Okay, that's all we got. Take a look at your practice and let me know what questions you have.